Let's return to looking at complex numbers, and we'll start off with the moivres theorem, which is this. Cos theta plus I sine theta to the power of n is cos n theta plus I sine n theta for all integers n. Now that's actually de Moivre's theorem. It's pretty limited in its use because we'd rather have something like this, which really it extends to it anyway. R times cos theta plus I sine theta. Really all it's saying is something we already know anyway, is that when we raise a complex number to the power of n, we raise the modulus to the power of n, but we multiply the argument by n. That's really all de Moivre's theorem is saying. So for example, 1 minus I to the power of 5. Now I could work out its modulus, root 2. I can work out its argument, minus pi on 4. So root 2, the cos of minus pi on 4 plus I times sine minus pi on 4, all of that to the power of 5. We raise the root 2 to the power of 5, but we multiply the argument. So we get minus 5 pi on 4. And I can easily work out root 2 to the power of 5 is 4 root 2. The argument, minus 5 pi on 4, I'll rewrite that as 3 pi on 4 because we like to leave things in the principal argument if we're going to leave it in that form. If I did want to work out what that actually is, then let's work it out. Cos of 3 pi on 4, sine 3 pi on 4, well that's minus 1 on root 2 plus 1 on root 2, multiplies out quite nicely. We get minus 4 plus 4i. The advantage of doing that, it certainly becomes very useful as that power gets bigger and bigger and bigger. I mean, to expand out 1 minus I to the power of 5, I suppose that's not too bad using our binomial theorem. But once that power starts getting up there, you're going to have a lot of terms to work out. And this probably is a quicker way of doing it. It does, of course, rely on us being able to work out the argument nice and neatly to do that. Oh, and the other thing I should say, if I'm leaving my answer in mod-arg form, change it to principal argument. Over here where I was actually working it out, I didn't really need to change it to 3 pi on 4 because of course the cos of minus 5 pi on 4 will give me the same answer anyway. So if I'm going to end up in Cartesian form, then I don't really have to worry about changing the argument. This can extend even further again and allows us a way of finding the roots of complex numbers. Because we now know that if z to the power of n is r cis theta, that's the answer. If I go back the other way, then I'll just divide by the n for the argument. And we'll get the nth root of the modulus. But you'll notice I've added in this 2 pi k, because when we're finding roots, there's going to be more than one answer. So I need a solution for every possible answer. And how do I do that? Well, if I go round the circle 2 pi, I'm in the same spot. And that's why we add on the multiples of 2 pi here. And I just add on as many multiples as I need to get the correct number of solutions. If I'm finding the root of a real number, hence all the coefficients would be real, it means the solutions would be in conjugate pairs. Because I'm just entering consecutive numbers, it's smarter, rather than going 0, 1, 2 and so on, to go 0 plus or minus 1, plus or minus 2, because that'll bring out the conjugates straight away. I want to find the square root of 4i. Of course, we've got a couple of different ways of finding the square root already. Here's another way. 4i I could rewrite as 4 cis pi on 2, which means z will be 2, that's the square root of 4, cis pi on 2, but I'll add in that 2 pi k. I need two solutions, so if I substitute in 0 and 1, I can get two answers. And so there they are, 2 cis pi on 4, 2 cis 5 pi on 4, but I want them in Cartesian form. I end up with root 2 plus root 2i and minus root 2 minus root 2i. I could have picked any two consecutive numbers I like and I would have come up with the correct answer. It just makes sense to use 0 as a starting point because that's an easy number to substitute in and then go from there. The other way I could do it though, if I just find that first solution, see, I don't worry about the 2 pi k, and I'll end up with the 2 cis pi on 4 and I'll plot that. But I know solutions will be symmetric as we go round. Because I'm finding two solutions, the next one should be 180 degrees away, so it's down there, and there's my other solution. I'm just adding that on. So you could think of it graphically as well. I'm going to find the fourth root of 16, and when we were just doing real numbers, we ended up with two numbers, of course, that could be, plus or minus 2. But there are actually now four answers. You see, 16 I could rewrite as cis 0. So it'll become 2 pi k, well, plus 0, don't write the plus 0 down. I want four solutions. Because it's a real number, I know the answers are going to be in conjugates. So I'm going to go 0, then I'll go plus or minus 1. I could have picked negative 2. I went with positive 2. Kind of makes more sense to go with a positive. But there's my 4 answers. So substituting that in, 2 cis 0, cis pi on 2, cis minus pi on 2, and cis pi. That ends up being 2, 2i, minus 2i, and minus 2. You see what I mean about it brings out the conjugates with the plus or minus. See, I've ended up with cis pi on 2 and cis minus pi on 2. Graphically, there's my first solution, 2 cis 0 or the number 2. I know they're going to happen every 90 degrees. So there's the next one, 2 cis pi on 2. The conjugate will be there as well. And then over there's my 4th one. Explains why, before we knew about complex numbers, and if I'd said to you, what's the solution to x to the power of 4 is 16, you would have said plus or minus 2, because they're the ones that are on the real number line. And they're the only ones you knew existed. The others were there, you just didn't know they were there, because all you could see was the real number line. The other 2 were still there, we just didn't know about them. Okay, let's find the 4th roots of 1 plus root 3i. Okay, 1 plus root 3i would be 2 cis pi on 3. So it would be the 4th root of 2, then it'll be pi on 3. It's not a real number, so I'm not going to worry about the plus or minus. I'll just go 0, 1, 2, 3. So 4 consecutive numbers. Subbing in, we get this wonderful expressions. 4 root 2 cis pi on 12, then 7 pi on 12, 13 pi on 12, and 19 pi on 12. As I was saying, if we're going to leave it in mod-arg form, then we use the principal argument. So I'll change those 13 pi on 12 and 19 pi on 12 down. If I was to look at it geometrically, the first solution, there it is over there, 4 root 2 cis pi on 12. But again, every 90 degrees, every pi on 2, there's a solution. There's my next one, my 3rd one, and my 4th one. And we can quite clearly see now why they're not conjugate pairs. Because I'm rotating 90 degrees, they will never line up vertically when I'm doing this. And they all sit nicely on a circle. Radius 4 root 2. Whee! Ooh, there we go. So 3a is looking at de Moivres' theorem.